hit record on this computer. And then
Emma, can you hear us on Zoom okay?
yes.
Sweet, we can hear you. You're on the owl group, so I don't know, sneeze or talk to your cat or something weird.
Hi, everybody. For those of you who don't know me, my name is Matthew Alford, and I actually did my PhD in scripts also in this lab. And many years later, came back and was part of sort of forming the mod group. So I'm one of the PIs in the mod group, and I've really spent a lot of the time that I've been here working on this EPSI capability that we are really excited about. So I was psyched to talk a little bit about the history of how it kind of came about, and I'll go even further back just to sort of talk about, because microstructure wasn't invented at Scripps, but it definitely had some of its very, very early days at Scripps. And so I'll tell a little bit of that story. I always start with this movie. This is actually by another Scripps researcher named Craig Winters. And what this is he put dye into a numerical simulation. And what you're seeing here is the dye getting sloshed around as an internal gravity wave comes in from the right and hits this sort of, idealized continental slope. And the idea here is just, how are we ever supposed to understand this, right, with the tools that we have? So the reason I love showing this is that you see the complexity, right? You see these layers, they're getting swept out. Imagine this is a tidal cycle. So every 12 hours, this sort of thing is repeating. And you have these breakers, and you have these tiny little filaments of mixed fluid, and you've got convective instabilities, shear instabilities, and it's all kind of happening at the same time, and it's evolving and sloshing back and forth. And so in the old days, with microstructure profilers, you would basically sort of get one profile in a few hours, and you wouldn't really know where you were, and you wouldn't see any evolution. And so you had to make all these kind of inferences. And so what we're trying to do, sort of my holy grail would be, could we ever actually make enough observations to understand a really complex flow like that? So just to make sure we're all on the same page, I know you guys have had days and days of theory and practice of microstructure by now, but the main reason we care about turbulence in the ocean, right, is because it actually moves stuff around. It modifies the properties of whatever water it's acting upon. So this is the equation for B. This is something like buoyancy. You can think of it as temperature or, kind of inverse density or something like that. And, this is the thing you guys all learned about in one of your introductory fluid mechanics classes, where if I put say this is a blob of cream in my coffee. If I want to wait, so eventually molecular diffusion will cause that blob to spread. And in fact, that's actually the only thing that can actually cause gradients to actually diffuse. But because the surface area of this is pretty small, you have to wait a long time. And so turbulence is really good at stretching and straining these things out. So you have the surface area increase and you get this huge thing. So what we try to do is we try to quantify all that by saying, okay, if I'm the buoyancy of this fluid parcel, and I know this quantity called the buoyancy flux, the turbulent buoyancy flux now in this case, I would say then that following this fluid parcel, the total derivative of buoyancy would be proportional to the divergence of that quantity. And then what we usually try to do is we try to use Fick's law to say, okay, well, maybe the buoyancy flux can be parameterized as a turbulent kappa times a buoyancy gradient. And so then you get this. But that's only true if kappa is constant in space, right? And so that's actually really important. Okay. And so then also two more people in our group, Arnaud Leboyer and Nicole Kudo, have done a lot of work in actually making turbulence something we call an essential ocean variable. And so this is something now that you have this sheet of paper and you can take to your NOAA people or your funding agents and say, no, it's essential. We have to measure turbulence. You guys know all this too, I think, but one of the main reasons we care about turbulence in the ocean, at least in the old days, and I think there's a lot more reasons now that we can talk about a little bit later, but this is probably already like a 10-year-old pair of climate simulations. And so what Bob Hallberg, who's at the Geophysical Fluid Dynamics Lab at Princeton, did is he ran 2 climate simulations. You guys know that climate simulations have typically, grid sizes of tens of kilometers. So there's 0 chance they're ever going to resolve turbulence. And so we have to parameterize it with these diffusivities. So if you take 2 climate simulations, and in one of them you add a little bit of artificial kappa, trying to simulate, unresolved turbulence, you get this huge difference in the temperature. This is the difference in the temperature between the two models. So the one with a little bit of extra diffusivity has a much, much warmer and broader thermocline because you're getting more heat flux down from the atmosphere. So that's really important. And then as you guys hear more and more about things like seafloor mining and even things like marine carbon storage, any scheme for storing carbon in the ocean is going to have to know a lot about the mixing. And I don't think that community even knows that yet. Okay, so how do we actually measure mixing? Again, you guys have spent a few days talking about this, so I'm just kind of, you learn by hearing it again and again. Okay, so if we, this is in some ways a simplified version of the movie we just saw. So this is a paper that Ali Bashayek wrote a few years ago called Goldilocks mixing. And what he did is took direct numerical simulations. Okay, so these are now really, really resolved. And he started with just a shear instability. So water's going this way, water's going this way. You start to get these roll-ups, and he's just plotting density here. And so you see at an early stage, you have this kind of billow that's formed. And you can imagine this would be pretty gravitationally unstable, right? Because you've got dense water above light water. But then it takes a while before turbulence actually kicks in and these secondary instabilities, and eventually you get all this mixing, okay? So again, the reason why we've been spending so much time making these cheap and easy to deploy profilers is that once again, in the old days, you would go through one of these things one single time, and you wouldn't know whether you're here or whether you're here or somewhere in between. And this actually matters because, have you guys learned about Thorpe scales yet?
Well, then
You will in week 3. Okay, advanced topics. So there's ways you can actually, so in terms of how you measure mixing, you can infer mixing by saying, oh, okay, well, looks like turbulence pushed some dense water up about this far, and it moved some warm water down about that far. And I know how stratified the ocean is, so I can estimate how much energy that took. And so I can use that as an estimate for how much turbulence it is. But it's interesting though, because if you do that, you would infer that there's some turbulence here, where in fact, this isn't turbulent yet. So it's later in the history of the breaking event that you get turbulence. Okay, so you can use those kind of indirect methods if you don't have any turbulence profilers, and you can go even more indirect than that, because we know a lot about how internal gravity waves break and lead to turbulence. And so these things called fine scale parameterizations are where you can estimate shear in the ocean on sort of 100-meter scales or something like that and estimate how much turbulence is happening. But that's got a lot of assumptions involved. So when you get out to these methods that we'll be talking about today and that you've been talking about in the class, you're talking about much more direct methods. However, even those aren't completely direct. So sorry for the busy slide, but I did want to kind of just walk through, I know you guys have seen this too, but how we actually estimate turbulence. And not one single one of these is actually mixing, except maybe this one. Okay, so there's 3 methods. And have they covered this already? Osborne, Cox, and Osborne?
touched on it, yeah.
Touched on it, okay. So one of these methods starts with what's called the turbulent kinetic energy equation, okay? So I can do a Reynolds average on the equations of motion, and I can write down equations for the turbulent kinetic energy. And then I would get this expression if I throw out about 9 terms, okay? So if I assume that there's no time dependence and there's not a lot of lateral transport of stuff, then I get this thing, which is, this is called shear production. So this is saying how much energy the turbulence is getting from the shear. And then, so that's the energy that's going into the turbulence bank account. And then the buoyancy flux, if it's a stratified fluid and there's mixing being caused, the buoyancy flux is always going to be taking energy out of the turbulence, right? Because it's having to do work to increase the potential energy of the system. And then this is dissipation, where you're actually adding very slightly to the internal energy of the ocean. So you're actually heating the ocean very slightly. It's just that that's such a tiny term in almost the whole ocean that it never matters for actually how much you're heating it, but it does take energy away from the turbulence. Okay, so this is what we actually measure with these shear probes that you'll see if you haven't already. I'll show you those in a minute. And the way we do that, this is what they look like. They're these piezoelectric beams, right? That if you deflect them, you get a voltage. Okay. And then you have to do that very carefully too. This is actually a wave number spectrum of the shear, which is what these shear probes are measuring. And they have these theoretical forms out to the small scales, and then noise always kicks in. And so there's a lot of kind of art and magic to how you know where is okay to integrate all the way out to. But again, going to some of the theory that you guys have had, this horizontal scale or this vertical scale is called the Kolmogorov wave number. And so that's the smallest scale where turbulence can exist. So that's method one. And so again, we measure epsilon. We don't know anything about this. And what we want is this, right? And so there's one little magic trick that Osborne 1980 did is he said, okay, well, what if these things are actually in proportion to each other? And that's called this flux Richardson number, or sometimes you'll hear it called the mixing efficiency, slightly algebraically different. If we make that assumption, then if we measure epsilon, then we can get this buoyancy flux just by this constant number. Okay, so we kind of tend to think of this as the gold standard for how to measure turbulence, but it's important to remember there's actually a lot of assumptions here too. And throwing out all those lateral terms is probably okay in the middle of a thermocline, but maybe if I'm working near a sloping boundary or something like that, we need to worry about that some. Okay, then Osborne-Cox is even older. This is now saying this was actually done before they could even measure shear with airfoils, and we'll get to that in a minute. Osborne-Cox says also throw out a bunch of terms, assume steady state. In that case, the production of temperature variance is then going to be equal to this dissipation of temperature variance, and that's what you're measuring with these tiny little thermistors. And so then, under those assumptions, you can actually then back out what the diffusivity is, which is related to the buoyancy flux. So that's method two, but again, lots of assumptions. This doesn't work near fronts. It doesn't work if you are in a thermohaline steppy staircase, for example, etc. Okay, and then the final one is actually the best one in some ways, and that's just saying, okay, well, we know that the buoyancy flux is actually defined as this correlation between vertical velocity and buoyancy perturbations. And so if we could actually just measure those and just take a long-term average, then that in some ways would be the best. The problem is that both of those are dominated by internal gravity waves too, so you have to average a long time. But you'll hear us, I guess I'll show you in a minute. We're also developing this little velocity sensor that we call the TTV, or travel time velocity sensor. And so that'll give us W prime. And then we have these thermistors to give us B prime. So we're hoping in our group to start making those measurements really, really soon. Stop me with questions if I'm making no sense. Okay, so is it right? I think it is, there's a lot of evidence that away from boundaries, these methods have been fairly vetted to within a factor of 2 or so. And the reason we know that is that there have been really amazing studies back in the 90s where they put a big cloud of tracer in and watched it evolve. And if I put a cloud of tracer in, you guys could show this from the buoyancy equation that if there's turbulence kappa acting on it, then the second moment it basically spreads it out slowly, right? It's spreading this out in time. And so you can make those calculations with the tracer, and then you can go in and make the microstructure measurements, and they tend to get within a factor of 2 or so. So that's good. But again, and then in the buoyancy, in the surface mix layer, there's another trick, which actually Ankita's paper is kind of dealing with, that if you know the buoyancy flux in the surface layer and there's no real shear, then that has to kind of equal, that all has to be kind of dissipated. And so that's another kind of way that you can check these methods. Okay, so a little bit about the history. So this really all goes back to this person named Grant. And he built this kind of wacky little sort of toad fish. And this is even before airfoil probes or before shear probes. So there they were using these things that had been used in atmospheric research for years, called hot film anemometers, and there were cold film anemometers too, where you're actually cooling it. And these things were great. So you're essentially saying, okay, I'm applying a constant voltage to this thing to try to keep it a constant temperature, but the flow is varying, so it's cooling it, and I can measure the voltage that I need to apply. So those are great, but they actually had a lot of issues. During this work, though, it was discovered these theoretical turbulence spectra that I showed a second ago. And so this is what I was plotting in that other picture, where this is this vertical wave number spectrum of shear, and this is this person Naismith. The year before I was born. you know, where you have this theoretical form, and then this wave number is the Kolmogorov wave number. So that's what we're always trying to measure with our instruments. And then finally, really, this is Tom Osborne kind of figured out how to make these biomorph beam shear probes work in the ocean. And they turned out to be a lot better because they were much less temperature sensitive than the other methods. And so really, I mean, that's what we've been doing for like 50 years. I mean, that's how we've met. We haven't really stopped measuring turbulence that way in all that time. And then on the thermistor side, these used to be made by this company called Thermometrics that was going to be bought by General Electric, but the market is so small. So this actually is the most expensive thing. You know, we make everything in-house here for our turbulence profilers. Those little biomorph beams that we buy, I think, are like $4. These that we then have to pot in glass to keep them from seawater. The little thermistors are $250. So that's actually one of the biggest, most expensive parts on our Epsilometer. So if you guys know any friends who make these things for much cheaper, let us. And then so that's that. You know, there were all these different versions. There were kind of a half dozen of these groups in these, more or less in these countries, that really had these parallel capabilities. And they were all a little bit different, but they were also they shared a lot of features in common. Essentially, what you need is a nice, stable vehicle, and your sensors are down here. And one of the biggest problems we always have is, okay, my shear probe wiggled, right? Was that the ocean or was that my vehicle, right? So that's one reason why you can't do these measurements from like a CTD from a ship, of course, because then you're transmitting all these vibrations from the ship down the wire. So they're all free fall or loosely tethered. And then you know, and then they have these sensors here. And then the other little trick is that, you know, these are accelerometers these are essentially like forces that are, sorry, these are accelerations that you're measuring. And what you actually, and the forces on the vehicle are constant. And so F equals ma, you want a really big, massive vehicle so your vehicle doesn't move quite as much. But that's not, when you guys are out on this prowl, you'll see deploying a big, massive vehicle is also kind of annoying. So there's trade-offs there. So most of them kind of wound up looking like this because of kind of what I just said. It's nice to have a big, massive vehicle, but it's a huge pain to deploy it. And so also those big, huge untethered vehicles, you know, you had to go get a small boat and bring it back. And so you're really only going to do a profile every few hours. Whereas these tethered profilers now, of course, it's a loose tether, so you're not putting any tension on the vehicle, but it allows you to get the data back in real time. So that's great to know your instrument's alive, and you just haul it back so you can do really rapid profiles. So that's what those started looking like in the 90s. And then that's kind of when I came in, so I was Mike Gregg's postdoc, and he's the connection really to Scripps. So Chip Cox is a really very well known. He was actually a student of Walter Monk's. There's actually this famous photo of Walter Monk, and then his student Chip Cox, and then Chip's student Mike Gregg, and then Mike Gregg's student Jen McKinnon, and then Jen McKinnon's student Caitlin Whalen. So 5 kind of academic generations in one photo, and that was just before Chip died. But the point is, Mike, you know, he developed this technology, some of it at Scripps with Chip, and then he went to my old institution, Applied Physics Laboratory at University of Washington, and I was his postdoc. And so I was up there playing on a boat with this instrument, and it wasn't exactly my fault, but I was on board, and I felt horrible because, you know, the vehicle was chopped in two when the ship ran over it. And there went $300,000. And that was no fun as a postdoc. So that is really, honestly, I was still scarred by that experience. And so that's more or less, so then the cell phone industry, the mobile electronics industry happened, and everything just got so much cheaper and easier. The reason it was $300,000 is there was, back in the corner of that lab up at APL, there was this kind of grumpy old guy named Earl, and his job was to like solder all these parts onto all the circuit boards, right? And it took months. So nowadays, we send these electronics boards, we design them digitally, Sean does, and then we send them off to a company. It's robotically, you know, digitally printed, and then it's robotically populated with all the components. So now this whole thing is what we refer to as an EPSI. Maybe let me just grab it really quick. And this is about $2,000. I won't pass this around, but I don't think I'll pass this around because this actually is supposed to work. They probably don't want the PI touching it. Okay, but so this is kind of hot rodded. Okay, so what this is we've got the pressure case, and then essentially there's all the analog electronics to amplify the signals, and then there's the digital electronics to store them. And oh yeah, perfect. And then this is a titanium pressure case, so it can go to about 2,200 meters of depth. And then what we love about it is it's totally modular. So this actually can take batteries, and so we could just stick this on a mooring or at a UV or a glider or anybody who will have us. Or we can, this is the same thing that we then put into our profiling vehicles, or we can put it on a wire walker. And so what this is you'll see these are the shear probes. And if we have time and they're done with the inspection over there, so Becca, the fabulous Becca, actually, she's actually making a round of shear probes right now. So you can see that. And then this is this other technology that we've had here called the travel time. Very simple principle, right? So these are just two megahertz transducers, and they're just pinging back at forth at each other. And if the sound takes longer to go one direction than the other, then there's a flow in that direction. And so we measure this to a time precision of 20 picoseconds, 20 times 10 to the minus 12. And that allows us to get these incredibly precise and low power velocity measurements. So that's that this now is really, if I were to drop this, we'd both be bombed, right? But it wouldn't be as much as we wouldn't be as bombed as if I ran over a $300,000 incident. And so that's really kind of how we do it now. So we've started sticking these on the Argo floats, the wire walkers, the deep solo floats, which is the deep version of Argo. We put these on gliders. We put these on underwater UUVs, and then what you'll see. But did you show them the FC fish already?
That'll be next.
Okay, so you'll see it on the next tour. But essentially, then this is our fancy high-speed electric winch. This goes way out past the ship, so again, keeping things away from the propellers. And then what you can't quite see here, but I'll show you a photo of in a minute, is this thing we call the Epsi fish, which has exactly this on it, but it's got this vehicle that's allowing it to drop slowly through the water.
Do you have a cost estimate of that minus the labor?
Oh, the actual Epsi fish?
Yeah.
The Epsi fish, yeah, we do think now, because there's like a CTD on there, which you have to purchase, and that's like $13,000. So we think they're probably closer to $25,000 with all the labor and assembly and everything like that. But it's still a lot better than 300.
Oceanography ain't cheap.
Oh,
Yeah, if you haven't learned anything else from this course, then maybe that's the takeaway.
And we think that's really important too, because this actually was taken in this experiment we did really near the seafloor in 2,000 meters of water, and we were just really aggressive with it. We could just run it really close to the bottom. We have an altimeter on it, but still, we weren't that worried. I mean, we didn't lose it.
BLT?
That was BLT.
I crashed it.
So I thought I crashed it more than you did.
Yeah.
The scientists always crash it more than the engineers do, because the engineers know they have to fix it. But so that's one reason why it's nice to be cheap. And then the other reason we built this is that you can go out and buy something that does exactly the same thing as this from Rockland Scientific. It'll cost you a lot more, but you will then own the thing, and then you don't have to have this team of engineers doing stuff for you. But what we like about this is that when we come up with like the next wacky idea for something we want to do, it's a little bit different. We can hot ride it or do whatever we want. And then the final reason why it's important to have it cheap is that if we ever were to achieve my sort of evil vision of having turbulence measurements on all the Argo floats, or at least a large section of the Argo floats, these can't be $80,000. They have to be $2,000. And so, because an Argo float is $20,000. So that's kind of the philosophy behind it. Oh yeah, I meant to, that's right, I forgot how to slide. So this is the electronics. This is actually the very, very first one. It's almost 10 years old now. So it looks kind of a little more janky than our more modern ones. But they all have the same components where you're essentially amplifying these tiny little voltages that come from the probes. You do it as close as possible to the probe because you don't want to have, radiated noise interfere with your signals. And then you digitize it as soon as you can, and then you store it to SD card. That's basically what they do. And then this is our Epsi fish that you'll see. A lot of it's 3D printed. Again, we tried to keep it really, really cheap. But it has the same qualities as all those other vehicles that you saw in the photos. You need to have these drag screens that open, so it's basically like a parachute. and then it falls very slowly through the water and nicely controlled. And then they retract, so you can haul it back without a lot of drag. Yeah. So I think I'll skip this, right? Because Charlotte's, I think, going to talk a little bit about how these are made, or maybe not.
Yeah, so if Becca can show you guys the like normal insides of a shear probe, I'm only gonna be able to show you the weird version that I do, which is slightly different.
That's
So-
true. That's a little, so yeah, so it's, maybe it's nice to see this. So this, so the thing that we buy for $4 is this thing, it's called a piezoelectric bimorph beam. And all that means is that if there's a strain that's put on it, it generates a voltage. And so that's all we do. We try to heat shrink it a little bit, and then we basically pot it so that it doesn't get seawater on it, and then they go inside those long stings that you saw that on the end of the instrument. And so this is all done. The potting is done, with molds and things like this. It's actually, there's a lot of art to it. And then the way that I think you are going to do this later, right? So they do get calibrated here as well. And the way we do it is that there's a laminar jet of fluid, and so that force, and because the pressure head. And then basically you're just changing the angle of attack as it, and so you can use that to calibrate. I think Charlotte will show you some plots of how that works later.
They did that earlier, so.
Oh, you already did that. Okay, that's right. I saw that. Okay, yeah, so we build these things in house and stuff. So this is just an example. This was actually really cute. So this is an example of how we can kind of mess with these and hot rod them for our evil purposes. So same experiment. We're in 2,000 meters of water. It's called the bottom boundary layer experiment, right? So we didn't actually care about anything that was more than, like, say, 300 meters off the bottom. And so we wanted it to just plummet like a stone until we got near the bottom, and then pop the chute open. So we developed this capability to send a command down the wire, so it could. So it's basically turned into, from a parachuter where the chute is open the whole time, into a skydiver where it's falling fast until we tell it to open. So that's an example of the kind of thing we were trying to do. Yeah, I don't know. So let's see, we could get into tour mode at any time, but this is the instrument that I just showed you. And again, the idea here is to have, so it's integrating a velocity measurement over almost 4 centimeters. So it's not quite as small scale as these shear probes, which are, 1/4 of a centimeter, but it's very, very precise. And so it's really good for these W prime, B prime type measurements. And so some of the early tests that we've done on this system are just demonstrating that it agrees really well with other measurements. So we're pretty excited about this just about being done. And then this is another gadget that we've just built, and it's been tested once. We need to test it one more time. And so, if anybody knows what an Argo float is, a deep solo float, they're very different from Argo floats. They're basically round. So it's basically a hard hat, because that was the best way to have a protection for the electronics down at 6,000 meters. So they have this round glass sphere, and then we have taken it and completely transformed it. So that's the red part, is what we were sort of given with the CTD that goes on the side. And what we did is just added buoyancy and then added this thing. So we made it more or less like one of our turbulence profilers. And so now we can make turbulence measurements from these deep Argo flows. So we'll be using that a lot in the next year. Okay, and then the last one is just this little sort of like field of windmills that I'm charging lately is, if you think about like those early plots I showed you of how much turbulence evolves as it moves on. What I would really love to do someday is actually measure the evolution of turbulence. Like you want to catch it multiple times as it evolves. That turns out it's almost always really, really hard to do, because usually there's some flow that's sweeping the turbulent event past you in time, right? And so this is actually Alex Andreadis' thesis. So this is a drifting thermistor chain that we put in. And it's actually tethered to a wire walker. It's kind of wacky. But so all Alex is doing here is he's plotting the wind speed and the buoyancy flux at the surface. And then we had a bazillion thermistors on here. So we're just imaging the temperature of the turbulence. But because it's drifting along with the flow, in theory, we should be able to sort of image some of these structures really well in time and watch them evolve a little bit. And so you can just, I love showing this movie though, just because, again, this is, I mean, that first kind of gauntlet I threw across the table for how hard it is to really measure turbulence was a model. This is now observations, and I could watch this all day because I'm just fascinated by just the richness of these structures. So what you're seeing here basically is this is the surface mix layer. It was about 35 meters deep, and the wind is blowing really strong. So during this time, turbulence is kind of grinding away at the stratification at the base of this mix layer. And it's these structures that are actually doing it. Some of them actually are convective structures that came from the surface, and some of them are breaking waves on this sheared interface here. So it's incredibly complicated place. And then for those of you who are getting into this literature, this is usually called the transition layer, because this is the mixed layer, this is the thermocline, and then this is this region where we just don't understand. We kind of just throw up our hands because there's this transfer of momentum and properties between, but it's kind of done by all these processes at the same time, and it's basically a hot mess. So we're trying to have these drifting techniques to give us a better view of that. And then our last wacky tool, this is even wackier, is Aaron Thode is another professor here at Scripps. And he built this thing, this company, he bought this thing, but it's a company that basically built, we call it a buoyancy engine. And so this is how Argo floats go up and down, right? So it's just pumping fluid in and out of a bag. And so it can change its volume, which changes its density, and that allows it to go up and down. But this has a big bag and a lot of fluid, and so it can have a big payload. And so what we did is we said, so the way Aaron uses these is he has all these lights and cameras and acoustics and stuff like that on them to study biology and acoustics. And we said, well, wait a minute, Aaron, can we catch a ride? And so we actually dangled a bazillion thermistors, just like Alex is, from this float. And now this is drifting along with the flow, but before Alex's measurements were at the surface, and now this is actually following an isopycnal. And so now you can get these really cool images of, proxy turbulence. But now supposedly we should be really in the reference frame of the flow, and I'm hoping that we will be able to actually see that. Yeah, and then just a little bit of work. I mean, lots of different groups are starting to put these different sensors on different autonomous platforms. So it really is kind of a nicely democratized field. I mean, 90% of groups use Rockland, which is this company that makes these really nice turbulence profilers, and we're the kind of the exception, but we're all sort of swimming in the same direction and basically trying to get as many turbulence in the ocean as possible. So I think that's kind of it. There's a few. It's just sort of annoying that we're still doing this the same way we've been doing it for 50 years, and so I'm excited about Charlotte's PVDF shear probe that she's developed. I wrote this wacky paper 20 years ago with a fiber optic technique of doing this, but I never really went, further with it. The thermistors that we use are actually a little bit annoying because it takes about 7 milliseconds for the heat to diffuse through the boundary layer and then the glass bead. And so those are actually really slow measurements. So if anybody has any ideas for a much faster thermistor, Jonathan Nash built a thermocouple, which is much faster, but it's very noisy. So anyway, and then we've got our travel time. So I think there's a lot of room. It's an exciting time to be looking at turbulence. There's a lot of really fundamental questions, I think, that are unanswered, even though we've been thinking about this for decades. And it's a field that's really, really ripe for just kind of technological innovations like this stuff we've been talking about. So that's all I wanted to say. Yeah, thanks. And if there's questions, we can take those, and then maybe I actually don't hear much going on over there, so maybe we'll get.
I just figured with Becca, she's okay with us going and checking out the show.
Awesome. So any questions while we have slides available before we go over there? Yeah.
Just I was on a cruise once that we had one PMP, and there we didn't have a winch or anything, so we did what people did back on the day, which was like throwing it 3 times and like getting it with our hands. Do you know why people did that in the past?
Throwing it 3 times?
Yeah, I don't know if it was like to get statistical. Yeah. I don't know.
What would they do? So sorry, it's tethered.
It's just a
right?
rope.
Yeah.
And like we threw it, let it free fall, and then we get it with our hands.
Yeah,
When you
yeah.
don't have a winch and you have to have like manual labor. how would that
Yeah,
go?
you're basically a human winch, I guess. Yeah.
You haven't heard about this thing about throwing 3 times and like the
I don't understand what you mean by, what are you actually throwing 3
So
times?
Profile?
street profile that what people did back in the day and not
No idea,
nowadays.
no idea. I mean, it could just be they're trying to do a little bit of burst sampling. I don't know what the 3 was really aimed at, but maybe they're just thinking that, by getting 3 profiles at one time, it's a little bit better than just getting 1. But I've never heard of that.
They did that on Astro last year too.
3 profiles?
Yeah, I think it's just for statistics, that you just
Yeah,
want like
yeah,
a couple.
yeah.
Yeah, you just hold steady and throw it 3 times just to,
Yeah,
because it's hard too, because you drop it and then it's like you need to know when it's off, and it's like a lot of rope. It's like a lot of hauling kind of thing.
Yeah.
So, it's probably just
sounds exhausting.
Yeah,
That's-
I was always curious why like with in the mud cruises we just like do profile and like, we go wait whereas these other people.
I mean, for Sunrise, we also just did like VMP profiling and then we took off kind of thing.
And you guys had the fishing reel for that, right?
For Sunrise 22, we had the fishing reel. Yeah, so me and Kaiki and Kaylee crashed the VMP into the
Nice
bottom
work.
about 10,000 times,
Yeah,
I think,
yeah.
over a whole cruise.
Yeah,
Yeah, didn't break a single pro.
that's amazing that it wasn't more, right? Because you don't have any, like you guys will see this on your cruise, right? So you don't have, with the fishing reel, it's internally recording, right? So you have no real-time information. You have no idea how deep it is.
That one was supposed to hit the bottom.
That one was supposed to have crash guard, exactly,
Yeah, yeah.
which we won't do with this one.
Yeah. Yeah.
So I know we have had many conversations about how the FC has to be free falling. But then you're also mounting it on things that seem like they aren't free falling.
That's a awesome observation. Yeah. Was that the question, or just like what the what? What the what?
Wire walker.
Yeah. Okay, so right. Okay, so that wire walker. Okay, so totally true statement that the shear probes, they have to have a platform that's not vibrating and not and moving in a predictable way, or else it's just hopeless. So the wire walker is, you have some hope there, because if you guys have seen wire walkers in operation, right, they're basically glorified ratchets, right? So they're buoyant, but the way they get down is they kind of herky jerky their way down from the surface waves. Okay, so that's hopeless to try to measure turbulence on the way down. But on the way up, it's essentially just sort of free rising. And so at least there's a hope that those are much better. And actually Devin just and Arno just have a paper, and Drew, of course, showing that actually works pretty well. However, it's not as good as one of these free fall profiles, because it's still loosely coupled to this wire. So I think it's kind of banging into the wire every now and then and things like that. So the noise floor is a little higher with the wire walker. However, so yeah, but you also hear people just bolting these things to CTDs and all sorts of stuff. So gliders are amazing. Now, gliders are actually one of the most hydrodynamic platforms of all, because they're totally untethered. They're just optimized for low drag because they run on batteries, right? So gliders are an awesome way to measure shear turbulence. But even if you want to just bolt an FC onto a mooring or a lowered CPD from ship, you can still use the temperature measurements, because those actually aren't sensitive to vibrations. And if you guys have heard of Kipods or Kipod moorings that Jim Mohm has really put forth a lot, those are just temperature. Those are FPO7s, exactly like these. So it's basically like an FC. They call them Kipods. They're not even trying to measure shear, because they know the mooring is just getting blasted all over the place. It's vibrating like crazy. But the temperature measurements they can make good sense of. So yeah, so that's a really good question. Yeah.
Has there been any other stuff done with fiber optic, or just what you looked at?
I don't know if anybody else has tried to do this particular thing, measuring turbulence. There's a guy named Ray Schmidt, not Schmidt with a D like you'd expect, but it's SCHMITT. And he and some other people were looking at using fiber optic, just refractive index measurements to actually get density.
Mhm.
But it was a larger measurement, so it was a sort of a larger scale measurement for
Okay.
not for turbulence, but for but I'm not sure where that actually went. So yeah, a couple things. And then the other part about fiber optic, which is unrelated to any of this, is Drew uses this technique called distributed temperature sensing, and I'm starting to use a technique called distributed acoustic sensing. So totally different. It's where you've got maybe like a C4 cable on the, there's a, communications cable on the seafloor, and I'm blasting a laser into it. And the reflections of the laser back along the fiber tell me the temperature and the strain.
Hmm.
So you can infer turbulence things out of that, but that's really totally different. Yeah. So, yeah.
I wasn't asked about the laser techniques, but is what you just said, the laser techniques.
This bullet point that says laser techniques on your slide.
Oh, it's just generic laser technique. Freaking laser beams. Yeah.
Lightsaber.
Actually, no, there's another class of these that I didn't mention. So actually, Jules Jaffe is another researcher at Scripps. Anybody know Jules? His lab is just up there. So he's been looking at things like, can I basically do PIV, or particle image velocimetry? So I can basically make a laser sheet and then try to measure the turbulent motions with that. So actually, he's got one of those, and then he's got another one where he's just basically looking at. He's got a strobe and just looking at cameras and trying to put together the flow field that way. So that's what I meant, I think, in that random bullet that I probably maybe didn't think about. Yeah. Want to go see some shear probes? Okay. And one more thing, I'm actually this is a shameless plug. Thanks to Camila, I'm now giving the Scripps Caspo seminar on October 15th. And I'll be talking about a lot of this sort of stuff. So you guys,
Anyone's around.
if you like, yeah.
Emma, I'm gonna disconnect the owl here and then see if I can take you with us to the to look at some things.